So, Vera, we're now ready to start. If you're ready, and I will introduce you. So I'm pleased to welcome our next speakers, because this talk has two speakers: Vera von Burg from ETH and Guang from Microsoft, and they're going to be talking about quantum computing enhanced computational catalysis. And my moderator helping with the questions in Slack for this session is Alexi Riley. Take it away, Vera. Thanks very much.
Okay, thank you very much for the kind introduction. So in this paper, what we wanted to look at was how and whether quantum computing can help us in the elucidation of the reaction mechanism of carbon dioxide fixation. So, which is a process that takes carbon dioxide to methanol. And this process might become very relevant in the future with rising CO2 atmospheric levels. So what I'm going to talk about in this presentation is how we even study such a process. And so this is called computational catalysis, and how and where we can employ quantum algorithms and what are the requirements on those algorithms. Then I'm going to quickly talk about how we convert the molecular or the chemical problem into something that we can solve on a quantum computer. And then Guang is going to talk about advances we have made on the quantum algorithm side and show you some resource estimation. So, and I hope you can see all my slides, right? Okay, good. Okay, so at the core of chemistry, as you probably know, are reactions. And we understand reactions in terms of their energy profiles. So if you have a certain set of starting materials that get converted into a product, if we know the energies of these two participants, we can determine their relative stability by knowing the relative energy differences between them. Furthermore, participants in such a reaction are usually separated by an energetic barrier, which I've indicated here. And we can obtain this energetic barrier by obtaining the energy of the so-called transition state, which is just the state at the top of the barrier. And knowing these energy differences, so these barrier heights, will enable us to compute the reaction rates of the reactions. And this tells you something about how fast the reaction proceeds. So now here we can already see an important aspect, because these energy barriers enter in the exponent for the reaction rates, which means that we will need to be able to obtain them with very high accuracy. And then other important aspect to mention here with respect to classical methods is that although with classical methods we can obtain such energy profiles, in some cases, they may have either a large or an unknown uncertainty associated to their respective values, which is of course not good. So it would be a really quantum algorithms would offer a high advantage if they can give us reliable error estimates on those energies. So being able to describe just individual reactions doesn't really take you very far. Instead, if you really want to understand the mechanism of a process, you have to look at numerous such reactions. And I'm showing you here this example of the catalytic cycle that we looked at in our paper, which is a ruthenium-based catalyst that was synthesized in the Leitner group, which can mediate this transition of CO2 to methanol. And so how you would then study this process in general is shown here. So first you would have to come up with some hypothesis on your mechanism. For example, what I've just shown you before, the catalytic cycle. And then you would have to determine the energy profile of all the involved reactions. And we hope to do this by a quantum computer. So what we have to do is first, for each of the involved intermediates and transition states, we have to convert them into some representation that can be used on a quantum computer. Then the quantum computer gives us reliable and accurate energies. And after some corrections, we can perform kinetic modeling. And we would then know, for example, how efficient our catalyst is in transforming the CO2. And we might also find out how we can optimize the catalyst, which would then mean that we would, of course, after optimizing the catalyst, have to repeat the whole process again. So this already leads us to a first set of requirements on quantum algorithms. First of all, it's not enough to just determine the energy of one single configuration or structure. We have to be able to do this for multiple structures. We have to obtain the energies to high accuracy, and this accuracy is usually given as 1 millihartry. And note that total energies are usually in the range of kilohartries. And furthermore, if quantum algorithms can give us reliable error estimates, they offer a real competitive advantage over classical algorithms. So now let's zoom into how we actually obtain those energies. And I'm going to focus on just the electronic energy here. And we obtain it through solving the electronic Schrödinger equation, which I've shown here, which is an eigenvalue equation for the Hamiltonian operator. And the Hamiltonian operator just contains the kinetic energy of the electron and the interaction terms, so electron-nuclear, electronic, and nuclear-nuclear interaction. And we evaluate it for a fixed set of nuclear coordinates. And the hope is that we could, provided we have a good starting state that has a good overlap with the true ground state, the hope is that we can use quantum phase estimation on the Hamiltonian to obtain the ground state energy. Now, as you may notice, this is a continuous equation. And in order to make this more manageable, we have to break it down. And we do this by discretizing the problem. We discretize it in terms of, by introducing a finite set of basis functions, which are so-called orbitals. And I'm showing you here some examples for the system we actually looked at. And for this system, these basis functions, so we have around 2,000 orbitals. And note that, so these orbitals are 2 electron functions. And we would represent on a quantum computer each 1 electron function by 1 qubit. So you have to double the number of orbitals to get the number of qubits you need to represent the state. So solving the equation in the full orbital basis is quite complex, even too complex for quantum algorithms, which is why we have to truncate the problem further. And we do this by focusing only on an orbital subspace, which we call the active space. And this active space is supposed to describe the essential chemistry in a very compact way. And in our study, we have selected 3 different active space sizes for each system, starting from a very compact one of around 10 orbitals and ending with a one that has a bit more descriptive in terms of the chemistry of around 60 orbitals. And so this, and I'm just showing you some example numbers for the systems we looked at here. I'm showing you the active spaces in terms of number of electrons and the number of orbitals. So, and you see that these active spaces range from 52 to 65 orbitals. And I've shown here what are called at the classical limit. So this means that these active space sizes are accessible by classical methods. However, it is very time consuming. And also they have, as I mentioned before, the associated uncertainty to it. So it will be very interesting to see how the quantum algorithms perform for these sizes of the active spaces. Okay, so now after having introduced these bases and these basis functions, our Hamiltonian gets transformed into this form. So it is a sum over terms which contain the so-called 1 electron integrals and 2 electron integrals. And if you remember the previous form of the Hamiltonian, you may notice that the 1 electron integrals now quantify the kinetic energy of the electrons and the electron nuclear interaction on a per orbital basis, whereas the 2 electron integrals do the same for the electron-electron interaction. And to understand how we can input this to a quantum computer, it's important to see that these so-called fermionic creation and annihilation operators that we have here can be mapped to strings of Pauli operators. So this means that through this introduction of this basis set and the selection of these active spaces, we have transformed our Hamiltonian into a sum of terms containing as weights the electron integrals and then the Pauli strings. And we can use this as an input to quantum phase estimation. And Guang is now going to tell you about the details of the algorithms we used and the advancements we made. So we're just going to switch.
All right, thank you, Vera. So the main workhorse algorithm that we use to get these energy estimates to very high accuracy and high precision is quantum phase estimation. So to give a brief recap, the idea is that if you have a unitary that encodes the phases of some eigenstate, for instance, maybe the eigenstates of a Hamiltonian, then you can use quantum phase estimation to get this phase to some error. The basic idea is that you apply the control unitary many times in a geometric progression. And overall, if you apply this unitary on the order of, say, n times, then you get the error of the phase to on the order of 1 over n. So in the case of Hamiltonian simulation, where you want to do time evolution by a Hamiltonian, this unitary would just be the Hamiltonian exponentiated times some step size, which we call the inverse of alpha. Alpha would have units of Hartrees, and is a bound on the energy spectrum of the Hamiltonian. So if you wanted to get the energy to one Hartree, 1 milli-Hartree, then the number of queries you must make to this time evolution step is going to be on the order of the inverse step size alpha times pi over sigma. And there are various tricks you can do to reduce this by constant factors. So we could certainly use time evolution as the unitary we use in phase estimation. This is the tried and true method that many papers in the past have studied. But then recently there have been new ideas. It turns out that it works just as fine to implement a unitary whose spectrum is 1-to-1 to that of time evolution. For instance, if you to estimate an eigenphase that is maybe the sine inverse of phi, that's the same information as getting the eigenphase of phi, because you can apply the sine function onto this phase as a classical post-processing step and still obtain the same energies. The main benefit of using, say, qubitization to implement this weird unitary that has this arcsine spectrum is that it contains the same spectral information as time evolution, but then it can have different properties compared to simulating time evolution itself. For instance, in the standard circuits used to encode this arcsine of the Hamiltonian, compared to, say, traditional methods for simulation like trotterization, there's no approximation error involved in applying the circuit. A trotter approach would have an error that scales with your step size, but this is exact. And you also get a different cost trade-off. For instance, trotter approaches would have a very small number of qubits, but then you would have no way to tune the number of non-Clifford gates. With qubitization, it's possible to get a trade-off between qubits and non-Clifford gates, and this has been used to great effect in a lot of previous works on simulating chemistry on a quantum computer, such as by in the earlier talk on Monday by Dominic, Barry, and co. The main idea behind qubitization is that of a block encoding. A block encoding is a unitary where you have somehow embedded this Hamiltonian divided by the step size in the top left corner. So top left meaning that if you apply this unitary on a joint quantum state where you have, say, an ancilla, maybe in the 0 state, and your chemistry system of interest, you will project this quantum state onto this Hamiltonian divided by the step size if you're to measure the ancillary resistor in some known states. And the great thing about the block encoding is that there are many, many ways to block encode a Hamiltonian, and all of them turn out to be more or less conceptually straightforward. For instance, a typical approach is using something that's called the LCU lemma, standing for linear combination of unitaries. if your Hamiltonian happen to be represented by a sum of unitaries, then a simple circuit to do this block encoding is to create a quantum state where all of the coefficients of your Hamiltonian are the amplitudes of a basis state, and a select unitary, which is basically controlled on, say, the jth index in your quantum state. Apply the, say, the jth unitary representing your Hamiltonian in this sum. Then if you apply SIP preparation followed by circlet, followed by preparation inverse, you have block encoded your Hamiltonian. This is the basic idea that we use to block encode the fermion Hamiltonian that we saw earlier for chemistry. But to do so, we need to introduce a variety of approximations in order to optimize the cost of the algorithm. The reason is that the overall cost of the algorithm is going to scale the number of queries that you use to implement this qubitization routine. So in phase estimation, we have the norm, which is alpha, divided by the target error, which is, say, 1 millihartree. Then we have to multiply this by the cost of this block encoding. And more or less, the cost of this block encoding is going to scale with the square root of the number of bits, classical bits, you need to represent your Hamiltonian. So if your Hamiltonian has a very dense representation, then you need a lot of bits. And so it works well if you can find a representation that is sparser, or in this case, to use more precise wording, a representation that is low rank. So initially, we started with the unfactorized Hamiltonian. That's what Vera showed you on the last slide. Here you have a sum over these two electron hopping terms, fermion operators AP, AQ, R, and S, and you have these coefficients H, P, Q, R, S. This two electron tensor in the worst case can have n to the power of 4 terms, where n is the number of orbitals. And in 2019 work by Dominic Berry et al., they studied different representations. In particular, they looked at the single factorized representation. This is a representation where you reshape your two electron tensor as a square matrix and perform an eigen decomposition, followed by truncating eigenvalues that are small. So in other words, you get a low rank representation. And the benefit of this approach is that now the number of terms has been reduced. Typically in chemistry, one finds that the number of rank components you need scales with n. So in this case, the number of terms has gone from n to the power of 4 to the rank times n squared. Because when you have your eigenvectors of this reshaped two electron tensor, you can reshape it back again into a symmetric matrix, and then that has n squared terms. So you can go one step further and further factorize this one electron term, this L sub PQ, by taking the eigen decomposition and also truncating the small eigenvalues. So this double factorized form representation has popped up numerous times in the past in chemistry literature, so we're definitely not the first to consider it. But then it turns out that there are a lot of technical difficulties in trying to block encode this efficiently. But the benefit of this approach is that in addition to having this dependence on rank, which could be small, scaling with, say, n rather than n squared, you now also have a dependence on the number of eigenvectors in each low rank representation of this one electron term that gets squared. So we can call this psi, and the number of terms is now rank times n times psi. In the worst case, all of this is just n to the power of 4, but in typical chemistry examples, these can be much smaller than expected. Some papers claim that psi scales with log n, but there are also many other papers that find out that for some systems, psi scales polynomially with n. So it's very system dependent, but if you find a good system, you can get a number of terms that scales all the way from, say, n squared to roughly n to the power of 3. And in addition to reducing the number of bits you need to represent your Hamiltonian, the other advantage of using this factorized forms is that you are in some sense partially diagonalizing your Hamiltonian. So when you have a matrix and you diagonalize it, its spectral norm is going to be the difference between the largest and smallest eigenvalues. And this is usually the tightest bound you can get compared to any other bound, like maybe the one norm of your Hamiltonian. So the cost of our quantum algorithm scales with this alpha, this norm of the Hamiltonian. And it turns out that by going from the unfactorized to double factorized approaches, you get a much smaller norm. So in other words, the number of steps you need to apply in phase estimation goes down. In this double factorized format,
sorry to interrupt, you have about 5 minutes left.
Right, in this double factorized format, we can also do a further simplification. It turns out that what you get is actually a sum of squares of free fermionic Hamiltonians, where each fermionic Hamiltonian is just simply a sum of number operators. Then you rotate these number operators by a given rotation. And the goal now is to block encode this whole thing. So before we get there, one of the insights that we had is that if you want to do this low rank truncation, to use a triangle inequality, you get tight bounds, but then it turns out that if you assume that all of these terms that you truncate have an error that adds up more or less randomly, you can truncate by a sum of squares, and this turns out to give you error bounds that seem to match the empirical bounds you get from the MRG calculations. So in our block encoding strategy, we can start by saying that first we have as an input a block encoding of the free-fermion Hamiltonian. So in other words, you have H sub R, the free-fermion Hamiltonian of the R rank component, and you have it in the top left corner of some unitary U sub R. The two electron interactions, those are squares of free-fermion Hamiltonians, so you can square with two queries. In the terminology of quantum blocks, you are computing the second Chebyshev polynomial of the top left corner. And then now you can take a linear combination of all of these squared free-fermion Hamiltonians. That gives us the two electron interactions. But in order to do this, we have to come up with a better block encoding of the free-fermion Hamiltonians. The main idea here is that when we have the givens rotated Hamiltonian and number basis, the insight is that you can split this into a sum of rotated number operators, where rather than performing the givens operation, which has n squared gates all at once, you instead rotate these number operators one at a time. So each given rotation now it just only has n gates. And the basic idea is similar to that of the earlier block encoding strategy. You have state preparation to encode the coefficients lambda. Then you have a select circle that is made by implementing this controlled number operator unitary, which is in the end just a bunch of controlled Z operations. And you have this multiplex givens rotation where controlled on, say, the index J, you apply a givens rotation that rotates just the J number operator. And this implements the free-fermion block encoding. And the advantage of this approach for encoding the free-fermion Hamiltonian is that we can use ancilla-assisted approaches for preparing quantum states. So rather than using, say, D quantum states for dimension D, instead of using D quantum gates for dimension D quantum state, you just use square root of that. Then the advantage of using these givens rotations that rotate number operators one at a time, rather than the givens rotations that rotate all of them at a time, is that it turns out there are tricks to implement this using much fewer quantum gates as well. Square root with the number of rank components times n, compared to if you do it all at once, which is square root of rank component times n squared. So using these approaches, we managed to reduce the resource estimates from what people have had in the past by orders of magnitude. In the very first approaches by Reiher et al., for this nitrogenase compound, we worked out that you needed on the order of 10 to the power 21 T gates, provably, to simulate this 1 millihartry, and this will take a very long time. But over the years, this has been brought down now to our latest result, which is also obsolete, to just 10 to the power 10 gates, which is 1 week of runtime on a more reasonable clock cycle of 100 kilohertz. So we applied this to all of the different molecular representations in the cycles of carbon capture. And then we find out that the empirical scaling of Toffoli gate counts with orbitals is roughly n to the power of 3.23. So it could still be improved, but then it's really within the realms of realistic runtimes that you could have on future quantum computers. So looking into the future, we found historically that progress in algorithms tends to beat progress in hardware. For instance, in a certain linear programming benchmark, we had like an improvement of 43 million, and 1,000 of that came from hardware and 43,000 came from algorithms over 15 years. Today, we hope to see something similar. If you look at hardware, in the past 4 years, we've seen a 10 times improvement in physical qubits from 5 to 53. But our progress in algorithms has also increased much more dramatically, a factor of 10,000. So as useful applications require a large number of qubits from hundreds of thousands to millions, one would hope that if we follow this trend, we would have further progress in algorithms and further progress in physical qubits to perhaps run these in maybe the next 10 years. So with that, I open the floor to any questions.
Thanks very much, Guang. So please do enter your questions in the Slack. I can see some people are currently typing their questions, but Alexei, while people are typing, do you have a question you'd like to ask?
Yeah, great. So thank you both very much for your great talk. So I had a question regarding your phase estimation algorithm. I was just wondering, how do you actually prepare a good trial state? Because obviously you need an overlap with the true ground state to collapse to a good eigenvalue. And if you have a multi-determinate ground state, it can be quite hard to prepare.
Right, that's a great question. So we know that in the worst case, preparing the ground state of Hamiltonian is a QMA hard problem, which is really, really hard. So this really now depends on peculiarities of the system that you're studying. For instance, is the Hamiltonian you're looking at, is it a worst case Hamiltonian, or is it more of an average case, moderately hard only to prepare? So we did DMRG calculations to figure out how hard it is to prepare these ground states. Like if you were to make a simple trial state, what would be the overlap with the true ground state? And it turns out that for these examples, the true ground state actually has a very large overlap with a simple, say, single configuration trial state. We'll call that the Hartree-Fock state. In particular, for all of the examples we studied, the overlap is on the order of, say, 50%, which is surprisingly large, but it's important to remember that there can always be worst case Hamiltonians. But so far, it seems like for these interesting problems, we are more on the average case, which is a very useful piece of information to know going into the future.
Okay, great. Thank you very much. Yeah, it's very clear.
Thanks, Guang Hao. So the first question has come through. We've got a question from Andrew Gu, who's asking, he says he might have missed this, but did you say that, I think it's a Greek letter C, capital C, I might be wrong, do correct me, Alexei, or Guang Hao if I've got that wrong. Did you say that this scales up to n cubed for the doubly factorized representation, whereas the singly factorized version scales as n squared?
Right. So C has a worst case bound of ON. It has, in some empirical cases, it appears to be log n, but then those are a little bit questionable. In the single factorized case, the number of terms corresponds to this worst case. You can think about it as being equivalent to this worst case ON. So if we were to refer to the earlier formulas, number of terms in single factorized is R times n squared, whereas in this double factorized is R times n times C. So in the worst case, they have the same number of terms, but in the best case, the double factorized approach could be more efficient.
Thank you. So we have about a minute left. I can see some people. There's a question that's just come through. So thank you. This is a question from Earl Campbell. Can you comment on the coherent versus incoherent truncation procedures? Because that slide went by quite quickly.
Right. So in the past, when people decompose quantum circuits into primitive quantum gates, people would perhaps use a triangle inequality. If you have an error in one unitary and you apply this unitary n times, the error just adds up linearly. But then, if you're to take a more average approach, there are papers showing that you can just add up these errors by a sum of squares, assuming that all of these circuit elements are in some sense random. And so you can reduce the error by this square root factor in the number of terms. So here we apply a similar idea. When we truncate our Hamiltonian, we can assume that all the errors of these terms, they add up linearly by a triangle inequality. But empirically, if you just add them up by a sum of squares, you get an error that more closely follows what you get from exact calculations of these ground state energies. Like if you were to truncate terms, you contribute an error to your ground state energy estimate, and it turns out that doing this sum of squares matches the ground state energy estimate much more closely. You get almost a linear fit with a coefficient of 1.
So thanks very much.